Like we ended up having a solution, a numerical solution for the Blasius equation. We still have the same solution here. So this lecture we are starting to talk about what that means. Now let's talk about. So this is exactly the same code we finished up last lecture. So let's try to interpret the solution. I zipped it and posted down. So the y-axis is. Some of you asked the x-axis, but we are going to be keep working on the code, so I'm going to be zipping it again and post it again later. So let's first run it to see what we get first. So it's the same code. We were in a hurry at the end, so let me put it in the proper format, and we'll be plotting. Let's review what we have been doing against eta at the end. So let's do this. Run at time. Okay, so we started all of this a little bit while by writing down what is the equation that governs the streamline any languages in a thin layer approximation. The equation we started with it basically analyzes the y derivative of phi, how much time which is spent on each x velocity code. So this is times actually spend several seconds calculating the derivative of phi to x and y. So this term, it's not negligible. It's not like you click the button and it pops up instantaneously. Translate phi to velocity. We have a motivation to figure out what is momentum spent on these few seconds. So minus we have this solution, which is very nice, and y velocity it looks also like the Blasius solution we have seen before. It looks like a laminar boundary layer. Translate very fast, but this is the y. We are going to do two things in the beginning of this lecture. One is to look at is there a way to solve it faster, and then to probe the solution to see if we actually not ux ue times due dx. And this is the pressure term. Let me zoom this in a little bit. Has to balance the x momentum transport term in the outside of the boundary layer. Sorry, no. I don't think so. Plus which room are you delivering the dissipation term. So that is the y derivative times kinematic viscosity times the second order derivative of psi. Okay. So this is and then we started by asking, seems to be able to increase it possible to have a self-similar solution. Here is that because that will simplify analysis, leading to understanding a lot faster. Is how much time is spent on this function, and a self-similar solution means the proportion is how much time is spent on subroutines of this function. There, when you shift, so we see like most of the time streamwise location from one position to a little bit downstream. Not its. The solution looks exactly the same except for a scaling. Not click on this. In the, I think we want to go back. The solution looks exactly the same like this, except for I have a scaling. So we click on this. Velocity. The font is still small. So it lists what the function is. It's a very short function. If you scale both x and y properly, the solution would look like exactly and now spending time in this one. So you can't see it. So that is that. Go back to the code itself and my solution at x plus dx. So the line corresponding to the epsilon times y. So y plus epsilon times y is a proportional scaling in the y direction. So would be proportional to the solution, right? Ux y. Discretized Blasius equation. And when we differentiate this, we get a differential relationship on the velocity u. Most of the time, so we set this plus theta y partial u partial y is equal to alpha times u. So this is derived by just the derivative of the what do you think is the computer spending time on interpretation of the self-similarity thing, right? It's actually solving a huge system. And starting from that, we can just write this u in terms of the streamline function, because u is who suggested 1,000 grid points. So just by substitution, we get the relationship in so 1,000 grid points, and we have three variables, so it's a 3,000 by 3,000 matrix, right? Is it big? Not really. Has to equal to so plus. What's the problem? Why is solving it taking theta y? So much time? So this is we can solve 3D Navier-Stokes equations with millions of variables. Okay, so let's start from here and specialize to the Blasius solution where alpha is 0. But we are only solving this for 8 times. I mean, you mean like when we're solving large equations? Where I get this equation? Okay, so this equation we get it by differentiating both x and y, differentiating the left-hand side with respect to x. The sparsity, right? So this the left-hand side being proportional to the x y means it is, right? This is equal to the structure. U all the times have a certain 1 plus epsilon prime. Are we taking advantage of the fact so when you shift towards the x direction? The U is scaled proportionally by a small amount. So the first thing we can do is to and the Y is scaled by a small amount if sparse matrices, right? That's what we mean by let's try that and see how much it can improve. So right now, this whole thing took you can see here, but took about 5 seconds, 4.7. The theta here is the derivative of epsilon with respect to dx with sparse matrix. Epsilon over dx. So the only thing we need to modify is epsilon prime inside dx. Actually, we don't need to do anything in this function because as long as we make these matrices to be sparse, the whole assembled matrix is going to be in sparse matrix format. Right. So now, here the first thing is instead of let me actually write it let's down. Actually start not with A. A is the most complex one. So let's start with B. Let me actually draw this. So instead of zeros, if I have a solution that is Blasius, and I have a solution later on that is also Blasius, I'm going to change all the zeros to sparse. Okay. The difference between instead of having an I which constructs a full identity matrix and UE of x plus dx, I construct a sparse is identity matrix scaled. So if this is dx, it's scaled by 1 plus epsilon to illustrate prime. So if you do zeros through, so basically zeros, UE of x makes a matrix with 9 zero entries. In the computer, it allocates memory for 9 numbers, and on each number it puts 0. That means if I take the derivative of UE with respect to x, this is going to be equal to epsilon prime over dx, which I call this alpha times UE of x. It only allocates memory for storing the size of the matrix. Is the rate of growth, and if you start to fill the matrix with non-zero entries, it only allocates memory for storing the I and j indices. Alpha equal to 0 means there is no growth, non-zero entry, and also the value velocity is of the non-zero entry. So that's a sparse matrix. Another thing is mathematically how does the Y similarity, how much memory it needs, and in terms of how much operation the computer has to go through. For example, again, to solve the equation. Take a look at the Blasius profile we get. So the Blasius profile is the same for the zeros is more efficient. For example, if you have a 1 by 1 matrix, the location of eta equal to 1 has to change. Bytes, right? So if eta equal to 1 is here, then eta equal to 1 is going to be a slightly shifted position in Y. Sparse matrix with eta equal to 2 here, then eta equal to 2 would be here. If you do a sparse matrix, right? You need to store the x, y. That change is reflected in this y plus epsilon. So let's say, so if you want to, if you y plus epsilon y matrix with the entry 1, the downstream profile corresponds to the same location as y. So you have a lot of additional housekeeping. And the rate of growth of that y is characterized by ij indices, right? So that's additional data you have to store. So let's say if the sparsity, if eta equal to 1 ratio of corresponds to a y total entry, if eta equals 1 corresponds to not low enough, then it's better to just use the full matrix. Let's say, and in our application, the bigger n the n use y here, the sparser the matrix is. So let me just say y eta 1. We have this location. N non-zero entries, a function of x. The size of the matrix is basically n squared. Where is the how thick is the boundary layer from here to here? So if you look up, eta equal to 1 corresponds to about 0.4 times the go to here. I think velocity. We have completed modification. Y eta 1 is basically how much further from the wall you have to go in order for the velocity of the Blasius profile to equal to 40% zeros and SPI then as opposed to if it is at x and this is equal to here, because then the theta is basically the next derivative of this to actually program something with respect to x. If your thing runs forever, that's not good, right? Okay, so so this is
B and C.
This is basically the slope of the same. So instead of zeros, I make a sparse. Not the slope, but like the only thing that is a little bit more complicated is A, right?
If
so
you extrapolate this slope,
we want to put it in, and MATLAB so that this has a very nice way
to the wall.
Then put
1 over theta would be the distance from the x location to where these two lines would meet.
It's different from diag because it can fill in multiple diagonals at the same time. So instead of having to have 3 lines, you can do this in 1 line. Okay. So
any questions?
For example, the first diagonal you fill in is this guy. So okay, so you need 4 arguments. The third and fourth argument is the size of the matrix. The first argument is what are the diagonal entries solution then to fill in. In this case, I have
connect
2 diagonal
two
entries,
lines. If you connect these
and I need to make them
when eta are both equal to 2,
so
then you are going back to the same
entry.
Right. Otherwise,
this is the second diagonal entry
solution.
Okay, so I basically put 2. So eta is
only
theta is a function vector
only
side by side
x,
and here it tells you which diagonal I want to put it in. So 0 is the
in the Blasius solution we see when we do the non-dimensionalization,
you shift it to 1 upper diagonal, so it starts with the 1, 2 entry. Right. So
I'm going to also interpret what
theta
means.
So this is what we need to do.
Actually, like 1 over theta, we are going to see that 1 over theta, which is the distance between x and the extrapolated
sparse of this
solution where all the tangents
this
meet,
one
is actually equal to 2
times
the distance from the leading edge of that plate.
Diagonals are going to be different,
so we are going to get to that conclusion by looking at
I have to
how this y eta 1
d
would
eta
grow as a function of x.
And this is
exactly
f,
from here.
And I have to plus 1 divided by d eta. And that's it.
Any questions so far?
Any questions on this? Right, just a
King
more
Shock,
powerful
I
function
think you
making
still
the construction even
looks
shorter.
like you are thinking about this data thing.
Let's try it. We didn't change any of the logic of
good.
the code. We just
now
changed a little bit of how to
now let's see.
So let's run it.
Before we analyze the more general solution, the Falkner-Skan solution,
so
which has a non-zero alpha,
let's
think of the Blasius solution, which is what we saw. That corresponds to alpha equal to 0.
It's 0.116 seconds as opposed to 5 seconds.
Alpha would be equal to 0.
It's great,
right?
And also it enables you to do this for much bigger problems.
So when alpha equal to 0,
now you can do.
Now we can
I won't blame you for choosing n equal to
a relationship for phi from this differential self-similar equation, and we did an integration in y to deduce a solution. Basically, integrating this, we can remove this derivative with respect to x, and by integrating this in y once, we can derive a relation that is going to get rid of that derivative in x. So once we do that, and we can also use the same relationship here to replace this with alpha times ue squared. So now every variable that depends on x is going to be gone, and we ended up with a differential equation that only depends on y. Right, so that's something we did on Friday before the last week. Okay, so we got the equation in y, and that equation looks like that. So the Blasius equation before the non-dimensionalization looks like this. So minus, so all the left-hand side, the convective term is going to reduce to minus theta times phi times the second order derivative of phi in y. The right-hand side, the viscous term, assuming nu is uniform, is going to reduce to nu times the third order derivative of phi. Okay, And from this equation, we can deduce that the solution depends only on y and nu over theta. Right, so the phi, with the boundary condition phi of 0 is equal to 0, d phi dy at 0 is equal to 0, and d phi dy at y equal to infinity equal to ue. So with this, we deduce that the solution would only depend on y, nu over theta, which you get by dividing both sides by eta, right? And also on ue. So that's what we got. And then we applied the dimensionality analysis to see how we can non-dimensionalize this equation. And that is also going to give us how this solution, particular solution we get, is going to scale in terms of both the x direction and the y direction. It is going to define what are the two coordinates we're actually plotting here. So with this solution, now we are going to go back to the non-dimensionalization to see what we are actually getting here. All right. So if you look at the units, y is in terms of a length unit. Nu over theta is in what unit? Okay, nu is always in L squared over S, right? That's the dimension of a kinematic viscosity. 1 over theta is what? 1 over theta is L, right? Because it's like the derivative in x, so it's 1 over L. Okay, that's good. So UE is in what? L over S, right? So that is going to help us define what the non-dimensional group we should be using to parameterize that equation. And one of the questions I got on Slack is that you did another equation with not just the parameters, but also the coordinates, the physical coordinates. I think is that Kinshock?
So this is the broader one, right? The question on the broader.
Right.
Yeah. Yeah.
Okay. So what you need to look at in a null space, the null space is a space, right? So you get 3 columns probably in the is it U or V matrix? In the V matrix, you get 3 columns. That 3 columns span the null space. So anything that can be written as a linear combination of these 3 columns is a member of the null space. So to justify the choice of, for example, y over L as a non-dimensional parameter, you only need to look for is the vector 1 and minus 1 corresponding to y and L can be written as a linear combination of the 3 columns in V you get. It does not require the vector 1 and minus 1 to be exactly one of the columns you get.
I guess the question was, how do you know which one, like which ones to combine?
How do you know which ones to combine? Look for the simple ones. In theory, you can choose anything. You can just use these 3 columns to parameterize your equation, your solution. That's perfectly fine. They are just complicated, right? It's just as if, like, the first time we did it, we derived a Reynolds number like thing that is 1 over the square root of the normal Reynolds number. That's perfectly fine. It is a linear combination of the only vector we get that defines the null space, right? So the normal Reynolds number is actually minus 2 times the vector we get, which is a linear combination. And that's the conventional thing we use as Reynolds number. But when you get multiple ones, then we have a motivation to look for the simpler linear combinations that are easier to deal with. So, for example, one way to define simplicity is sparsity, right? So if you can combine some of them to get as much zeros as you can, then you know my non-dimensional parameter can be written as the ratio or the product of very few quantities. in this case, we have the luxury of only getting one non-dimensional parameter, right? And this is the eta we are going to get. So, and in this case, it's pretty easy to do because y has a length scale, and nu over theta has length scales cubed over s, and ue has L over s. So if you divide these two, we can get rid of s. So nu over theta ue is going to equal to has a scale of what?
Just like square times
L squared, right? And now we have something L squared. We have something with L. So y divided by the square root of this L squared, which is nu over theta ue, is going to be non-dimensional. So we can define our solution to be psi to be a function of this. So this is the non-dimensionalization of the y space, and this y over this is exactly what we are plotting in the y direction. So what does here mean? What is this 40% mean? This 40% means when y is equal to 1 times nu over theta ue, my velocity inside the boundary layer is 40% of the free stream. Okay, so if you look at 2.8, we know that my y is now twice times that value. All right. Oh, of course, we also have a scale in this direction, and from the boundary condition, we know that as y goes to infinity, the phi should be ue. So this non-dimensionalization is basically phi divided by right. So we are actually plotting phi prime here. So the derivative of phi is what we are plotting here, and the derivative of phi here with respect to that eta is non-dimensionalized by ue, right? Okay.
I have a question on the previous page.
Yes.
So when you apply the boundary conditions here, you're applying a boundary condition on phi at 0, right?
Yes.
What if you were to apply the no normal flow boundary condition? So d phi dx, I guess. Because that gives you v, right?
Yeah, d phi dx equal to 0 gives me v, but that is already used. So when we are deriving an equation that gets rid of this d phi dx here, right? We already used the condition that phi at all x locations when y is equal to 0 has to equal to 0. So when we are getting rid of this, the d phi dx equal to 0 at the wall is used. As a result of using that, the equation we got has no x derivative in it. So it's not even possible to apply that boundary condition in this equation anymore. Right. So we only have a chance to apply the x velocity equal to 0, which is d phi dy equal to 0. All right. Okay. Now we have this similarity solution. We know eta equal to 1 means y is equal to that. But there is one thing not satisfactory. What is theta? Right? How do I know my local theta? Because theta can be a function of x. And what's amazing is that relationship, the same non-dimensionality analysis, is actually going to tell us how does theta change as a function of x. All right, so let's take a look at what this means. As we said before, if you look at boundary layer, this is x, this is y, over a flat plate. So the boundary layer grows like that. Okay, in a certain way. We assume we don't know anything about how the boundary layer grows, but the thickness of the boundary layer is going to be a function of x. And as a result, if I trace over all the locations where eta is equal to 1, so I look at the boundary layer here, the boundary layer is like this. Eta equal to 1 is about when this is 40%, so this is eta equal to 1. I also choose here, eta is equal to 1 to here. So let's say if I draw a line where this is eta equal to 1 line, okay, I actually know that this is the growth rate of this eta, like y eta equal to 1 actually grows like that, right? Does it make sense? This is how the y direction scales. And we know that if we plug in here, right, so y eta equal to 1 is actually equal to that. So we know that dx of the square root of nu over theta ue is equal to theta of nu over theta ue. All right. Make sense? So right. So there is a bunch of things we can do now. So let's look at what. So nu is constant, theta is not constant, and I wonder if this is the most efficient way to do this. This is probably not the most efficient way to do this. Let's take another approach. Let's actually, because I don't want to deal with square root, let's square both sides of this. So let's say y theta equal to 1 square is equal to nu divided by theta ue, right? I think that'll be a little bit easier to do. Okay. So that leads me to the equality that theta is actually equal to nu divided by ue times y eta equal to 1 square. So that gives me a theta as opposed to this. So now combine our knowledge with theta to our differential equation about the y eta equal to 1. That means ddx of y eta equal to 1 is going to be this times y eta equal to 1, which is going to cancel one of the squares. So I no longer get a square here. I just get y eta equal to 1 here. Right. So what does that mean? That differential equation about y eta equal to 1, if you have been dealing with ODEs for a long time, you can immediately see that is a square root growth, because I can multiply both sides by eta y by the y coordinate, and what I get is a y times dy dx is equal to a constant, right? It's equal to a constant. So that constant is going to be equal to half of the derivative of y eta equal to 1 square. Agreed? So that the y eta equal to 1 squared, which means the square of this blue line, is going to grow linearly as a function of x. The slope of the square of this line is constant. So that's what gives us, like, just from the dimensionality analysis, how a similarity solution, in the case Blasius equation, would grow as a boundary layer in X. Okay, and it also tells me if it started with with the leading edge, so that is the leading edge. Then my y is going to be 0 in the beginning. So it also gives me that y eta equal to 1 square is actually going to be equal to 2, the 2 I'm going to move to the right hand side, nu ue times x. Right, x is the location from 0 to any place.
Also, we already applied the boundary condition at the leading edge. That's why there's no constant.
Yeah, so here we are assuming the leading edge started with x equal to 0.
Right.
Right. So then we are defining the x to be the location on the flat plate relative to the leading edge, where the thickness of the boundary layer is 0. Okay, and you can do you can look at this equation and this definition, this equation where we got theta, right? So from this equation, we basically combine this equation with theta and say, okay, 2x is equal to 1 over theta. So theta is actually, we are saying it's a length, 1 over theta is a length scale, right? 1 over theta is a length scale that is actually, for a flat plate, is actually twice the distance from the leading edge. So in a lot of, how many people actually read the book, the Aerodynamics of Viscous Flows book, Professor Driller wrote?
I do not up to this part quite yet.
Okay, anybody else?
I haven't read this part yet.
So I encourage you to read this, but like Professor Driller started from almost the opposite of this approach. So he first used the thickness of the boundary layer to derive a relationship in X. So he looks at the macro growth of the boundary layer first, and then he derives the fact that the boundary layer has to grow in a square root way first, right? For Blasius equation, and for Falkner-Skan equation, it grows to a polynomial order. And then he goes into assuming, now I know that it has to grow like that, I put in the equation to derive the similarity solution. So here what I'm doing is the opposite. I'm saying if I have a similarity solution, it has to satisfy this equation. And then because of the way we non-dimensionalize this equation, the boundary layer has to grow in such a way. And if you do the other approach, there is this factor of 2 here. So if you do the other approach, you already know that the boundary layer grows as a square root of x. And so in Driller's book, there is a factor of 2 difference in what I'm describing here, because instead of using theta to non-dimensionalize things, he would be using x to non-dimensionalize the Blasius equation. So what you get in Driller's book is I think there is so after the non-dimensionalization, after my non-dimensionalization, nu becomes 1 and the theta also becomes 1. In Driller's non-dimensionalization, the nu becomes 1 and the theta becomes what? Theta becomes half. Okay. So that's a subtle difference you're going to notice. That is, different people. Some people have a half in the Falkner-Skan or Blasius equation. Some people don't, just because of the different approaches we are taking.
The choice of eta equals 1, is that just arbitrary?
That's arbitrary. You derive exactly the same equation. You derive this to be exactly the same using, let's say, eta equal to 2 or eta equal to any constant. Yeah, it's just a fixed location relative to the boundary layer profile.
Right.
Mm-hmm. Yeah, that's a good question, though.
So you could have chosen that to be at the thickness of the boundary layer.
I
it
could,
would perfectly match.
It would perfectly match. That's right. That's right. Actually, that's a very good point. So I can, I do think it's probably also very natural, maybe more natural, to instead of using y theta equal to 1, to use just the displacement thickness. Right. And we can actually calculate from this numerical solution what is the how does the displacement thickness compare to my choice of eta equal to 1, right? So we can basically integrate all the area over here to figure out how big is the displacement thickness delta relative to my y eta equal to 1. By the way, the displacement thickness is the integral of streamwise velocity minus the free stream velocity, okay, divided by the free stream velocity. So that's so I'm gonna write delta is gonna be equal to integral of from 0 to infinity dy of 1 minus u divided by ue. All right. So let's do a numerical integration here. So we have Blasius, and this is no longer one iteration. This is just a Newton's iteration. And after I plot it, let's do a integrate to get displacement thickness. So
non-dimensional thickness.
Yes, that's right. So I have my fp, that is my streamwise velocity, divided by, or it's already divided by ue, right? That's good. So I have just a 1 minus that is what we are trying to integrate. And what type of numerical method do we know about numerical integration? Trapezoidal rule. Can you tell me if I use trapezoidal rule to integrate this, what do I do? Let me say d is equal to that. So how can I integrate d using trapezoidal rule?
So you have your delta y's, and you have the list of fp's, right?
The eta, right?
Will just be 0.5 times d eta
Yeah.
times fp.
In this case, I'm integrating.
Plus fp minus.
Yeah, right. So that is a way to integrate a function numerically. So if I write it down in the space, so what I'm doing is u minus over ue. What I'm doing is actually so this is 1. I'm computing the d, and I'm using small trapezoids to approximate the area above this curve. All right. So the area of the trapezoid is half of this plus this times d eta. So this is what I'm doing. Right. Third, this is what I got. All right. So my displacement thickness is about 1.2 here, right? It's 1.2. That is about 1.2168 times where is it? Times times square root of that. Nu over theta ue. And if you like to use the flat plate x as opposed to theta, so it's this times square root of, so instead of 1 over theta I have 2x nu ue. All right. Okay, and if you factor this square root of 2, I think this is usually 1.72 is usually the number you see in literature when you about the Blasius boundary layer. If you use the Reynolds number based on the chord length, so you take the square root of 2 multiplied by with the 1.2, and what is rest is square root of x nu divided by ue, which is the Reynolds number based on the distance to the leading edge, right? All right. Okay, so let me 1.7208. So it's actually square root of x nu ue, which is 1.2708 times. Yeah, I need to times x, and then it's nu divided by ue x. So this is basically 1 over square root of rex, right? So that's the formula you usually see in literature. All right. Any questions so far before we move to Falkner-Skan equations?
Can I just look at the boundary layer plot?
Yes.
So the 1.2168 is the eta.
Right.
Which
is like over here. So what this means is that if you take the whole block, right? So if you look at the total area under this 1.2, the area is going to be the same as this area over here.
So it's like the mass deficit thickness, right?
Yes, that's like the mass deficit thickness, also called the displacement thickness. Yeah. So the reason it's the reason it's called displacement thickness is because we'll study this later. Is that if you think of I don't know what's happened. Okay, so if you think of a streamline outside the boundary layer, the streamline outside the boundary layer is going to be the same for two cases. One case is that you have a viscous flow with a boundary layer with a displacement thickness defined in this way to be a certain function of x. The second case, the outside streamline is going to have the same streamline is if I have an inviscous fluid with no boundary layer at all, but the wall is displaced by a certain delta y that is exactly the same as the displacement thickness of the boundary layer in the first case. So the outside streamline is going to be exactly the same for these two cases. And that is going to provide basically the basis for our coupled boundary layer and in viscous flow solution we are going to study after we have a good handle of the boundary layer solutions. So the displacement thickness is a key quantity that goes from the boundary layer solution to the outside flow solution. Okay, so that's the way the boundary layer and outside is coupled. The boundary layer tells the outside flow solution what is its displacement thickness, and the outside solution is going to tell me what? It's going to tell the boundary layer solution what?
The pressure gradient.
The pressure gradient or the UE, right? I mean, if I'm solving this equation, it's the UE that matters. So this is how things are coupled. The boundary layer solution tells the outside my delta, and the outside tells the boundary layer the UE. Okay.
So in practice, how do you match the two?
It's gonna be like the coupled equation we wrote down in the last lecture. So in the last lecture, we wrote down four equations, right? 3 discretized equations plus a equation that describes the boundary condition. Now think of the whole system as just a two system of equations also coupled together. So we're going to write down a larger list of equations. Part of that describes what's happening in the boundary layer, and part of that describes what's happening outside. And we solve the whole system at once, for example, using Newton's method. So that's how things are actually coupled together. Right? That's a good question.
It's just a bigger matrix with...
Yes, it's just a bigger matrix.
With non-bilateral, bidiagonal terms?
Here we do have non-bidiagonal. Yeah, that for sure has non-bidiagonal terms. But even inside this equation, what we have, it's not the whole matrix. It's not a bidiagonal matrix. The whole matrix is a composition of. So the whole matrix we got. The whole matrix we got was a composition, was a matrix, a bidiagonal matrix here. If we are looking at the first solution, a zero matrix here and another bidiagonal matrix here.
Right.
And then we have something like that and something like that. And then the boundary condition has a 1 here and something like a 1 here and 1 here. Right? So this is the whole matrix we got last time. It's not bidiagonal at all. There are all these coupling terms that couples everything together. It's the same type of matrix we are going to get in the coupled inside-outside like boundary layer in viscous flow system. There are each diagonal block corresponds for example, how the boundary layer influences itself. So this whole thing is going to be like a diagonal block for that coupled system. And the outside in viscous solution is also going to have its own thing as the diagonal block. And then they are coupled with each other on the off-diagonal terms. For example, if the boundary layer solver is represented by what I'm doing here, it's instead of doing the integral formulation we're going to introduce later, we're just solving the thin layer Navier-Stokes. Then the coupling term from the thin layer Navier-Stokes to the outside would be what is going to be representing the numerical integration, right? I'm going to be integrating my u along the y-axis to give the outside what is my delta. That is going to be one off-diagonal term. All right. And another off-diagonal term is going to be now this entry, which in this case corresponds to the equation that my f prime at infinity minus 1 equal to 0. Now it's no longer minus 1 equal to 0. It's minus something that is provided by the outside flow field has to equal to 0. So that corresponding row needs to have another non-zero somewhere, right? Does that make sense? All right. Okay. So 7. Okay. So we discussed how this works for the Blasius equation, and did we derive the case when we have a non? Let me see. Did we derive when we have a general equation? Right. So we did derive when we have a general, when we have a non-zero alpha. What we are satisfying is a slightly modified equation, right? Okay, so when we have a non-zero alpha, when the UE actually changes as a function of x, we have a slightly modified equation. And the equation we would be solving is like that. Is we have an alpha, now is non-zero, times the, not derivative, times the first derivative of phi square minus alpha plus theta times phi, a second order derivative of y. Now this is the advection term in the momentum equation. A times UE square, so no, alpha times UE square. So that is my pressure term coming from the outside, plus nu times the third order derivative of phi. So this is the new equation we are solving. If we make all these three alphas equal to 0, it'll be exactly the Blasius equation. Okay? And this alpha corresponds, as we analyzed a little bit earlier, the rate of growth in x of the external velocity. So here, again, we can write phi as a function of u. And previously, the parameters are theta over nu and UE. Now in this case, we have one more parameter, right? we have one more parameter. Alpha and theta are the same unit, right? Otherwise, you can't add them together. So the additional one is alpha over theta. So this is already non-dimensional. So when you non-dimensionalize the coordinates y, you can still non-dimensionalize to the same thing. So y over square root of theta divided by nu ue. Can somebody check if that's right? I think still right. Yeah. Actually no. So it's nu over theta ue. And alpha over theta. So this alpha over theta serves as another parameterization of the solution to the equation. And after non-dimensionalization, what I get is, instead of alpha, I get alpha over theta, right? I'm just call this A. So what I get is A times this minus 1 plus A. So theta becomes 1, alpha becomes A, phi, not Y anymore, now it's eta, is equal to A times UE becomes 1, right? Plus nu also becomes 1. So third order derivative with respect to eta. So that's what we get. And just a slight rearrangement of the equation. Let's still define our f to be the non-dimensionalized version of eta. So phi divided by the appropriate scales. So in this case, I think you need UE times the length scale. So the length scale is what is non-dimensionalizing y. So f to be this, fp to be df d eta, and fpp to be the second order derivative of f with respect to eta. Then this equation becomes fpp prime, so that's this term, plus 1 plus a times f times fpp, plus, that's the additional term we are having, 1 minus fp squared times a equal to 0. So that's the new equation we are having. All right, so that's this is the additional term that comes out from here and here, and there is 1 plus a inside the f times fpp. So now let's go back to the.
Sorry, why is that a?
What?
Why is there, so 1 plus a, the bracket, what is there a plus in front of it?
Because we moved this term from the left hand side to the right hand side.
Oh, okay.
Yeah, so I should write 0 equal to that. It's clearer. Right. And also that makes this term to be the minus fp squared here. Right. Okay, so hope we have time to put this into MATLAB. Should we try? Let's do it. So here we go. Instead of Blasius, I'm gonna copy this and well, let me just rename it FS, Falkner-Skan. All right. So initial condition, let's keep them. The grid, let's keep it to be the same. Initial guess, let's keep it to be the same. And Newton's iteration, well, let me just take x equal to x0 to be here, right? So I mean, let me just make x equal to that. So it's just the initial condition. Newton's iteration, okay, now let's define my a to be, let's first make sure a equal to 0. We are gonna get the same solution. So my dg dx depends on A, my g depends on A, but anything else should be the same, right? Right? Okay, so dg dx, only this discretize the actual equation. The others are definition of FP and FPP, so they don't have to change. The boundary condition is the same, so only this one has to have an A, okay? And this one, I need an A in it. So before we modify the gradient, let's look at the actual residual. So it needs the A here, and the first needs the A. So let's first modify this equation. How do we modify that? First, we have a 1 plus A in the F times FPP. So let's put a 1 plus A here. All right. So that's the approximation to F times FPP. Right. Okay. But then there is a additional, let's say, Fs term. The Fs term is this additional one. It's 1 minus Fp squared times A. So we have A times, well, this needs an A. A times what? 1 minus. Remember, this equation is an approximation in the middle of the grid, in between two grids. So again, let's use trapezoidal rule to approximate F square. So not F square, Fp square. So Fp 1 to n minus 1 square. I need to have half Fp 2 to n square divided by 2. That's my new term, right? Okay, plus Fs term. That's it. Okay, that's my modification in the GA. Now I want to also differentiate this new term. To differentiate this new term, first of all, I need this factor of 1 plus A inside which lines? I think here. Right, so that is a differentiation of the 1 plus A term. And I think this is also a differentiation of the 1 plus A term. Otherwise, I think they are the same. Now we also have the additional term we called Fs term. That is going to give us a non-zero contribution in which matrix? Which are the matrices we need to modify to account for the 1 minus Fp squared term? So this is the derivative of the equation with respect to F. This is the derivative of the equation with respect to FPP. We introduced another term that only depends on what? Fp, right? Fp 1 minus Fp squared. So this equation is no longer zeros. Okay, so let's copy our construction here. It's still going to be bidiagonal, right? So let's copy the construction here, and we don't have the 1 plus A anymore. It's just okay, but we have a minus A times, right? Because we have A times and it's a minus sign. And if I differentiate this Fp divided by 2, I just get Fp, right? I differentiate Fp squared divided by 2, I get Fp. So this is Fp, and I don't have to divide by 2. I don't have 1 plus A, I have Fp, and I don't have divide by 2. I think that's it. I think that's all the modification we need to do on the Blasius equation to get a Falkner-Skan solver. So let's first get the same initial condition and run Newton's relation. I want to print out the residual, how the residual decreases. So let's see, residual is equal to G, because if G is equal to 0, I know the equation is satisfied, right? And every time I want to display the norm of the residual. Okay, the norm of a vector is basically a quantification of how big the vector is. If the norm is 0, that means the whole vector is 0. So let's try this. Too many input arguments. Oh, DGDX, I forgot to put in
A.
Oh yeah, I forgot to put in A. Okay, so let's try again. Oh, okay, this time it runs, and we can see that residual goes from 4 to 26 to 5 to 0.6 to 0.01, 10 minus 5, 10 minus 12. So that's the typical convergence of the Newton's iteration. So once it starts to converging, it's really fast. Now let's try A equal to 0.5. See how it works. Okay, still, you see, this is the last time. Now, because I changed the A, initially it has a big residual, and now it converges again really fast. Where's my solution? Okay, my solution is here. So now, what is the effect of a positive A? Previously, we said that eta equal to 1 corresponds to 0.4, right? Now it corresponds to something a lot faster. The boundary layer got thinner.
Thinner?
Thinner.
Thinner, right.
Yeah. A positive A means the UE increases or decreases as a function of x. Increases. Yeah. What kind of pressure gradient do we have?
Adverse.
Favorable pressure gradient. It thins the boundary layer. Okay, let's try it another way. How about minus? Let's run it. It did not converge. Okay? Did not converge. So we did something. I mean, of course, we get a non-convergent solution. So we did something too aggressive. So let's try something slightly less aggressive. Minus 0.1. Okay, we get a thicker boundary layer. Now, eta equal to 1 is now, and also we see that the curvature is not monotonic anymore, right? So you get a negative curvature here. Let's try something even more aggressive. Did I converge? No, I didn't converge. So this is also too much.
If it doesn't converge, does that mean separation? If it doesn't converge, does that mean separation?
If it doesn't converge, it means there is no, we didn't find a stable solution, right? So it's hard to say it doesn't have a solution, but at least it's very difficult to find. So we tried, it doesn't converge all the way anymore, but still doesn't converge all the way. But like you find this solution seems to be separating, right? So
can you increase the number of iterations to make it converge, or to see if it?
Okay, sure, that's a good point. So you said the 1.5. I'm going to try another one. Now it converged, right? And the solution looks like that. So what does this mean? In this, the UE goes negative, right?
Reverse flow.
It's a reverse flow for a portion of the boundary layer. So that's a separated solution. So that happens when I take my A to be negative, like negative 1.5. And remember, A is a ratio of alpha over theta. So theta is the rate of growth of the y scale in the as x increases, and alpha is the rate of growth of the UE as x increases. So a negative A means a negative alpha. So that's basically saying that the external flow decelerates as I increase in the x direction, right? So that's an adverse pressure gradient. So this Falkner-Skan solution actually you would never see in experiment because it's as you're getting close to separation, the flow becomes infinitely unstable. So basically it's impossible to even get a self-similar solution. I mean, you can do Falkner-Skan solutions by basically putting a wedge. So if you want a favorable pressure gradient, you make a wedge that is positively angled. If you do negative, you have to make a wedge that goes like that. But it's very hard to it's very hard to even get a solution that is have a small gradient, have a small stress. So this is this class of solutions we are going to see later. We are going to be using the Falkner-Skan solutions as a constructing block for our reduced order model of the behavior of the boundary layer. Okay, these are something like the basis of our construction. Any questions?
If you increase the resolution, the eta resolution, does that help with stability, like increasing and decreasing?
We can try, but I think 1,000 is a lot. So if we do that, and let's start with something easier to converge. Okay, it finishes. This is my solution, and we just tried. Let's do that. It converged, and 1.5. Try again. It converged.
I think you were at 0.2 or something like that.
Okay. No, it still failed. Let me try this again. It doesn't converge. So I initialized this and was not working. Right. So it's I think when the resolution is sufficiently high, then the problem is pretty similar as you further increase the resolution. So yeah. All right, these are good experiments to do, like playing with the numerics, getting good resolutions. So hopefully next week you're going to be doing this yourself. All right. Okay, I'll see you on Friday. I'm still not 100% sure we have the same room, but I will announce that when I'm sure.
Thank you.
Thank you.